Hello everyone, my name is Harriet Hartman. I am an exchange student from Croatia, currently studying here at Chatham National University, and I will present topic titled Principle and Perspectives of Hydrogen Production through Biocatalyzed Electrolysis. I'll start by providing you some background on the need for sustainable hydrogen production. Next, I'll discuss the principle of biocatalyzed electrolysis and how this technology works. After that, I'll cover the methods used in the study, followed by the results and discussion. I will summarize conclusions and give you some questions. The article is from the Journal of Hydrogen Energy, which was published in 2006. And the motivation behind this study is firstly a growing need for renewable energy sources as fossil fuel resources are depleting and climate change is intensifying. To address this, our study explores a new technology that uses wastewater for hydrogen production, leveraging the capabilities of specific microorganisms. The hydrogen produced through this method has the potential to replace fossil fuels with significantly lower energy costs, providing a sustainable solution. The core idea is that microorganisms oxidize organic matter, which generates an electrical current. In this setup, a biological anode and a cathode are connected through a power source, allowing hydrogen to be produced at the cathode. For our experiments, we used acetate as a model compound. Biocatalyzed electrolysis of acetate requires applied voltages that can be as low as 0.14 V, while hydrogen production by means of conventional water electrolysis in practice requires applied voltages well above 1.6 V, making this an energy-efficient process. On the left side is the anode chamber, where the biological anode is made of graphite, felt. Microorganisms oxidize organic matter, in this case acetate, which is added as the energy source. This oxidation reaction releases protons, electrons, and bicarbonate ions. The anode medium is a nutrient-rich solution with pH 7, containing everything what is written here. These electrons made an oxidation reaction flow from the anode to the cathode through an external power supply, which is necessary to drive the reaction. The power supply here applies a low voltage to facilitate hydrogen production. The cathode is a titanium mesh with a platinum coating. The cathode medium is a simpler autoclaved solution containing everything what is written here. In the center is a Nafion 117 cation selective membrane separates the anode and cathode chambers, allowing protons to move from the anode side to the cathode side while preventing the passage of other ions. Here the protons combine with the electrons arriving from the external circuit to produce hydrogen gas, where for 100% efficiency, theoretical, we need 1 acetate for 8 electrons, which would combine with 8 protons and give 4 molecules of hydrogen gas. It's worth noting that both the anode and cathode chambers are kept under anaerobic conditions. First, we have the electrochemical cell setup. The system consists of a 2-chamber cell made of polymethyl methacrylate, with each chamber holding 3.3 liters. Next, media preparation. The anode chamber is filled with an autoclaved medium that includes nutrients and acetate for the microorganisms. The cathode chamber contains a simpler autoclaved medium designed to facilitate proton reduction, moving on to electrochemically active microorganisms. The anode chamber was filled with microorganisms from a reactor that had been doing biocatalyzed electrolysis for over 5 months. After that, microbial growth was carefully controlled by adjusting the anode potential to create a stable microbial community. Finally, we have the experimental procedures. We applied voltage in gradual scans from 0 to 0.75 volts to measure current generation. Experiment was conducted at constant voltage of 0.5 volts with continuous nitrogen flushing in the anode chamber to enhance mixing. Starting with efficiency, we achieved a Coulombic efficiency of 92%, indicating effective conversion of acetate to electrons. The cathodic efficiency was 57%, reflecting the conversion of electrons to hydrogen. The maximum system efficiency we achieved was 53% at an applied voltage of 0.5 volts. Losses were observed primarily due to diffusion. A significant amount of hydrogen was lost through the membrane, and some energy was also consumed by the microorganisms themselves for growth and maintenance. Finally, the key challenge and limitation is cathode potential losses. Most of the voltage loss occurs at the cathode, where high overpotentials reduce overall efficiency. This graph illustrates the relationship between applied voltage on the x-axis and current density on the y-axis on the anode surface. Open circles represent current generation without electrochemically active microorganisms showing no significant current at any applied voltage. Closed circles show current generation immediately after inoculating the anode chamber with electrochemically active microorganisms. Initially, this inoculation alone does not produce significant currents. Current generation increases notably after a 5-day growth period, open squares, and a following 3-day growth period, closed squares. The similarity between these scans suggests a stable microbial community, indicating successful growth of electrochemically active microorganisms. These scans confirm that a mature, developed culture of electrochemically active microorganisms is essential for the current generation. The results also show that increasing voltage is necessary for enhancing current generation. To introduce this slide, let's review how the theoretical and actual voltage losses were determined in this setup. The experiment used a potentiostat to maintain an applied voltage of 0.5 volts while measuring the potential of each electrode separately through silver. Silver chloride reference electrodes in both the anode and cathode chambers. The theoretical voltage for acetate electrolysis requires a minimum of 0.14 volts. This is based on Gibbs free energy calculations for the reactions at pH 7, where the theoretical equilibrium potential for the oxidation of acetate is around minus 0.28 volts, and the theoretical potential for the reduction of protons to hydrogen is minus 0.42 volts. Taking the difference between the theoretical potentials for oxidation and reduction, we get minimum amount that acetate electrolysis requires minus 0.14 volts, while ideal standard conditions suggest a minimum of 0.14 volts. This slight increase to 0.16 volts accounts for practical deviations due to factors like solution concentration, minor kinetic barriers, and slight additional energy needs to initiate hydrogen production in a real system. In practice, the anode reached a measured potential of minus 0.22 volts by the end of the experiment, indicating a 0.04 volts overpotential loss. The cathode reached minus 0.71 volts, resulting in a 0.28 volts overpotential compared to the theoretical value of minus 0.42 volts. The reported overpotential loss is noted as 0.04 volts and 0.28 volts due to rounding and minor experimental variations during duplicate experiments. These overpotentials were derived by comparing the measured potentials with their theoretical values, indicating additional energy requirements due to limitations like resistance and reaction kinetics at the electrodes. This graph shows how the applied voltage of 0.5 volts is distributed among different losses in the system. At an acetate concentration of 2 millimole, the theoretically required applied voltage necessary to start hydrogen production is 0.16 volts. We can see that the largest portion of the voltage is lost due to cathode potential losses, as we saw on previous slide, with value of 0.28 volts. The remaining voltage of 0.04 volts is lost due to anode potential losses, as well as ohmic and membrane resistance. This graph demonstrates the relationship between current density on the x-axis and cathodic hydrogen efficiency, solid line, as well as diffusional hydrogen loss, dashed line, for the experimental setup in our study. The solid line represents the estimated dependency of cathodic hydrogen efficiency on current density. As current density increases, cathodic efficiency also increases, reaching nearly 100% at higher current densities. In the calculations, it is assumed 100% H2 saturated conditions apply in the cathode at all current densities. This suggests that higher current densities favor more efficient hydrogen production at the cathode. The cathodic hydrogen efficiency curve rises sharply at first, due to the low initial hydrogen production and relatively small diffusion loss through the membrane. As current density increases, hydrogen production intensifies, but diffusion loss remains constant. This makes the impact of diffusion loss relatively smaller at higher production rates, causing the curve to level off. Thus, the curve shape reflects an initial rapid increase followed by gradual flattening as the relative effect of constant diffusion loss diminishes. The dashed line shows a constant hydrogen loss due to diffusion, predicted at 4.1 liters per square meter per day. This loss remains steady across different current densities. It only depends on the hydrogen concentration gradient and not on the hydrogen production rates. The dotted line shows the hydrogen production at 100% cathodic hydrogen efficiency. The star represents the cathodic hydrogen efficiency achieved in our experiment. We see that it's not on the line of efficiency because the experiment was not conducted under fully hydrogen-saturated conditions, unlike the assumptions in the model. To conclude, biocatalyzed electrolysis has potential for sustainable hydrogen production. By using microorganisms to oxidize organic matter, this process can produce hydrogen from wastewater, making it an environmentally friendly hydrogen production method. System design improvements are needed. The current experimental setup has cathode potential losses and low hydrogen conversion efficiency, indicating that optimizations are necessary to make the technology economically viable. Reducing chamber volume and using better electrodes can increase efficiency. Decreasing the volume around the anode and replacing the current cathode with a gas diffusion electrode could significantly boost hydrogen production and reduce energy losses. Biocatalyzed electrolysis can also serve as an effective wastewater treatment. In addition to hydrogen production, this process could be a method for treating wastewater rich in organic matter. The technology has potential for decentralized applications. With further development, biocatalyzed electrolysis could allow individuals and industries to produce hydrogen from their own wastewater, reducing dependence on fossil fuels and contributing to sustainability.